Okay, let's get started talking about this second law of thermo and entropy. And here we'll just talk about entropy and what this second law actually is. And then the next section we'll talk about heat engines and the Carnot cycle. So entropy is simply a measure of a system's energy gained or lost as heat per unit temperature. So how much energy per change in unit temperature or per unit temperature does a system gain or lose? And our symbol for entropy is a capital S. And so you see delta S is equal to the final entropy minus the initial entropy, unless you're someone who enjoys calculus, you don't necessarily have to worry about this second component. But it's just the simply saying the change in energy per unit temperature. It's also a way that we measure or look at the different ways the atoms can be arranged in a system. We can really think of it as a measure of the disorder within a given system. In nature, we see that systems tend to move towards an increase in entropy. Things tend to get more random as the energy in the universe and in a given system tends to spread out more evenly. We're going to look at a couple different processes in thermodynamics. Some we call irreversible, and when the process is irreversible, the change in entropy is always greater than zero. And for reversible processes, it can be zero or it can increase. Reversible processes really are ideal scenarios. In real life, you don't have reversible processes because a reversible process is one in which you can get back to the exact same place you started without any change in the energy of the system. And we know that doesn't happen. But what you should notice is that the lowest value, even in an ideal system, that entropy can have, or the change in entropy can have, is zero. So you can never decrease the entropy in a system. And so what that means then is really that you're not going to have heat or that thermal energy spontaneously move from a cold object to a hot object. You're not going to have thermal energy flow down the gradient. We know that thermal energy always flows from hot to cold, not from cold to hot. And that idea is simply a reflection of this idea of entropy. If we wanted to move thermal energy from cold systems or from a cold object to a hot object, like in the case of an air conditioner or a refrigerator, we're cooling down something below thermal equilibrium, we have to do work on that particular system. And so then this brings us into the second law of thermodynamics, which says that if we have a process that occurs in a closed system, the entropy of that system is going to increase for our irreversible processes, and it's going to stay constant for reversible processes. And we're going to see where this becomes more important as we start talking about engines and heat engines and refrigerators, where we start moving energy, specifically thermal energy, from one place to another. And within this, we have what's called the Kelvin-Planck formulation, and this really you can read through the specifics of it, but it simply says that we'll never have 100% efficiency in any type of work heat conversion. Anytime we try and use thermal energy to do work, anytime we try and convert work into thermal energy, we're always going to have something that gets lost along the way. We're always going to be losing energy along the way. If we weren't, it would be like a perpetual motion machine. And as we know, that's not realistic. Just like when we're talking about motion or an object rolling along the ground, just like why we don't ever see an object roll on forever because there's always energy lost to friction. The same idea goes here. You're always going to lose something along the way, some energy along the way, when you convert heat energy into work or work into heat. And that's actually where we're going to stop for the moment. It's just a nice quick set. The next set where we start looking at heat engines and the Carnot cycle is going to be a little bit longer.